Good morning. My name is Koyal. I am going to give a presentation on first come first serve scheduling algorithm. So in this presentation, firstly I am going to briefly introduce about the topic that is first come first serve scheduling algorithm, and then I'm going to and now and next I'm just going to tell which are the components we have used in this in experimental setup, and thirdly I'm going to tell the implementation part, how we have implement the algorithm, and then we will see the observation. And lastly, we are going to I'm going to tell the comparative evaluation. So let's just see the introduction of first come first serve scheduling algorithm. So here, let's see the overview of the operating system. It is a fundamental function of OS that manages the execution of processor on the CPU. CPU scheduling is a key function of operating system. Determines the order of processor execution on the CPU, aims to optimize performance matrices like CPU utilization, throughput, waiting time, and turnaround time, ensure fairness, responsiveness, and efficient resource usage. So, what is first come, first serve scheduling algorithm? So, it's a non primitive. Once a process starts, it runs until completion. Processors are handled in the order they arrived, implemented using a basic queue structure, fair in order of arrival but suffers from the convey effect. So, what is the objective of this assignment is it's built a complete FCFS scheduling stimulator, handle dynamic arrival times and burst time, compute key matrices like waiting time and turnaround time, test the simulator on at least three data sets, and evaluate FCFS performance and its limitations. Analyze whether FCFS is suitable for real-time systems. So next, let's see the experimental setup. So here in experimental setup, I have used programming language that is C. This is chosen due to its efficiency, low-level control, and sustainability for OS simulator. Support structured procedural implementation of scheduling logic. Arrays and structures used to manage processes data. It also provides fast execution and precise memory handling, ideal for CPU scheduling simulation. And the tool is Dev C++ IDE because it provides integrated editor, compiler, and debugger, easy tracking of errors and variables. States supports validation of scheduling logic, simplifies compiling and running C program during simulation testing. So let's see the data set description. So multiple data set creates to test FCFS under different conditions. So let's see one by one. PID, which means processor ID. It's a unique processor identifier. The next one is arrival time, that is 80, time when each processor enters the ready queue. And the third one is burst time, CPU execution time required by each processor. And then waiting time, that is time spent waiting before execution. And then is turnaround time, total time arrival to completion. Next is complete time, the time at which the processor finishes execution. And the last one is starting time, which means the actual time at which the processor begins execution on the CPU. Let's see the implementation part. So here I have taken an example, which three processor, that is P1, P2, P3, and their arrival time is 012 and the burst time is 432. So let's just go step by step. First, we have short processor by arrival time. Like we have to arrange them in a increasing arrival time. So here, my example is already in a shorted form, that is P1, P2, P3. Then we will initialize the time variable. So the current time is equals to 0. Prepares arrays to store the following content, that is starting time, complete time, waiting time, and turnaround time. So in step 3, we will schedule each processor, means we will calculate the starting time, complete time, and turnaround time and waiting time, and we will update the complete time. So here the starting time for the processor 1 is 0, complete time is 4, means P1 finishes at 4 and at 0 P1 starts. Then we will calculate the turnaround time as complete time minus arrival time, which is 4. And waiting time we will calculate with the two formulas, that is starting time minus arrival time or turnaround time minus burst time, so which is 0. So then we will update the complete time as 4. Similarly, we will calculate for processor P2 and processor P3 as I did here. And then at step 4 we will compute the average matrices of average waiting time, which has KM as 2.67 and average turnaround time which is 5.67. So here is the calculation table, which contains three processor P1, P2, P3, and arrival time is 0, 1, 2, burst time is 4, 3, 2, and starting time is 0, 4, 7, complete time is 4, 7, 9, turnaround time is 4, 6, 7, and waiting time is 0, 3, 5 respectively. We will analyze the result as, so FCFS executes processor in order of arrival time without the preemptation. We are it is a non-preemptive algorithm. Means which first come, it will complete that work and then moves to the next work. Later arrival time processes, that is P2, P3, wait for earlier the processor, increasing their waiting time. The average matrices gives an idea of overall efficiency, showing FCFS is simple but can be less effective for shorter processor arriving time. So based on the above example, I have drawn a Gantt chart here. So here P1 starts at 0 and finishes at 4. And P2 starts at 4 and finishes at 7. And P3 starts at 7 and finishes at 9. So this is the Gantt chart of the problem. So let's just see the code of the topic. So here, the structure is used to store all the details of each processes like PID, arrival time, burst time, starting time, completion time, waiting time, and turnaround time. And here the parameter is giving as 5. Then will sorting passes by arrival time. FCFS must execute processors in the order by arrival. So sort by arrival means use bubble sort to arrange processor based on arrival time, ensures correct FCFS execution order. FCFS scheduling logic, which implements in the FCFS function, initialize current time is equals to 0. For each processor, start is equals to max of current time of arrival time. CPU may be ideal until the processor's arrival. Completion time is nothing but start plus burst time, and the turnaround time is completion time minus arrival time. Waiting time is start time minus arrival time, which updates the current time after each processor finish. Stimulates non-primitive FCFS behavior accurately. Next, the printing statement. Here, printing results and calculating averages. So here, in this part will print the output and calculate the average. So print result display a formatted table, that the table a table is inserted in this program. So through this line of code, the table will be created. That is printf PID, arrival, burst, start, completion, waiting, turnaround. So this line will create a table, which and also it will compute the average waiting time and average turnaround time, helps measures the efficiency of FCFS. This user input handling the main function. So next, the main function in here, the main function asks user to enter number of processor, or then after entering the number of processor, it accepts the PID, arrival time, and burst time for each processor. Stores all the input in an array of processors structured, and then calls the FCFS to perform scheduling. Print results, which shows the output. So, at lastly, the key feature of the program is implements full FCFS scheduling algorithm, handles dynamic arrival time, calculates all essential matrices, that is waiting time, turnaround time, starting time, and complete time, displays results neatly in tabular format, easy to extend for other scheduling algorithms. So let's see the output to understand it more briefly. So here is the output. First, we will enter the number of processors. They have given the enter the number of processors. So we will enter 3. Then it will ask enter PID for processors, that is P. Then they will ask arrival time. Then we will enter the arrival time. As like that only they will ask burst time. This process will continue for 3 processors. And finally they will give a table which contains PID, arrival, burst, start time, completion time, waiting time, and turnaround time. And at lastly, it will compute the average waiting time and average turnaround time. So what we observed from the previous code is given here. So we have taken an example in implementation part. So here the waiting time has arrived for P1 is 0, where the P1 starts immediately, no waiting. And then the P2 waiting time is 3, waits for P1 to complete. P3's waiting time is 5, waits for both P1 and P2. And then the average waiting time is 2.67 units. So what we observe from this is FCS favors earlier arrival processing. Processors arriving later suffers higher waiting time. So next, the turnaround time. What we observed in turnaround time is the P1 turnaround time is 4, P2 turnaround time is 6, and P3 turnaround time is 7. So average TAT is 5.67 units. What we observed from this is TAT waiting time plus burst time means longer waiting time increase turnaround time. Later processes experience higher TAT due to cumulative delay. So here the CPU utilization is total execution time is 9 units, no ideal item in this example. So 100% GPU is utilized. So at last we will see the comparative table. So here we have took three data sets, data set 1, data set 2, data set 3, and their processor, 3 processor P1, P2, P3, and corresponding average arrival time and burst time we have taken here. We will compute FSS matrix, that is in early slides I have told about the data set 1. Similarly, we will create for data set 2 and data set 3. Okay. So here is the comparative table of data set 1, data set 2, data set 3, and for all three data sets we have taken 3 processor, and the average waiting time is given here 2.672 and 2.67, and average turnaround time is 5.67, 4.67, and 6.33 respectively. So what we see is, so overall analysis we saw seen from this project from this comparative table is FCFS is a simple and fair executing process strictly by arrival time. Average waiting time fluctuates based on burst order. Short processor behind long ones, way higher waiting time. Long processor executes early, improved performance. Conway effect observed is long CPU bound processors slow down shorter ones. Turnaround time is closely tied to waiting time, especially when processor lengthy vary. So overall, I want to conclude the presentation by telling that if CFS works well when processor burst times are similar, performance improves when shorter task arrives after long task, not suitable for system where shorter or time critical processor must respond quickly. So thank you.